Chapter 8 is about equilibrium and elasticity. Interesting chapter. It's also kind of short. There's only 5 sections or 6 sections maybe. The first section is about torque, which we've been learning about, and static equilibrium. So static, as we've learned, means not moving. Dynamic means moving. So in this section, we're talking about not moving. Equilibrium means things are in balance. So we're not moving and we're in balance. And we're talking about torque. So we're applying a torque, but we're not moving and things are in balance. Okay, so we've spent several chapters talking about things that move. In physics, it's equally important to talk about things that don't move. So that's where the static part comes in. Buildings and dams must remain still, even with huge forces acting on them.
I hope so.
Otherwise, things collapse, right? Joints in the body must sustain large forces through supporting heavy loads or carrying heavy objects. Then dynamics is the physics of things that are in motion. Statics is physics of things that aren't in motion. Static equilibrium is achieved when the net force in all directions is 0 and the net torque is 0. So that's important. The net force in all directions is 0 and the net torque is 0. So right off the bat, we have a hint on how we're going to be solving problems in this chapter. Net force is 0, net torque is 0, and then those two things are going to help us to solve our problems. So in the picture, net force on the particle is 0. That means we have static equilibrium, and both the net force and the net torque are 0. So the block is in static equilibrium. So that means we cannot have any kind of rotational attempt here. So no net torque. And then the net force is still 0, but the net torque is not 0 in this third one. So the block is not in equilibrium in this case, okay? So this cannot be in C for us in this section. So moving on, the participant in a strongman competition uses an old-fashioned device to move a large load with only muscle power. The old-fashioned device is what you're seeing here. The 1 ton, so 910 kilogram bucket of rocks is suspended from a sturdy, lightweight beam, which is 0.85 meters from a pivot. The man lifts the beam at its end, 3.6 meters from the pivot, and holds it steady. How much force must the man apply, and what is the force of the beam from the pivot? So we see the picture on this side. The man is holding it. Looks like he's struggling. And then we have the pivot sitting over here on this end on the right-hand side. And then the large bucket of rocks is sitting over there. Now, if the rocks were closer to this end over here, he'd have a heck of a time lifting that up. So he's using the simple machine of a lever here to gain advantage, a mechanical advantage with the longer beam so that he can lift that thing up against this pivot on this side. So if we look at sort of a more like a free body, are you okay?
Yes.
If we look at, are you just making this up or what?
No.
Okay.
It's uncontrollable.
It's uncontrollable. All right. So if we look at more of like a free body diagram with, it's not really a free body diagram, but if we look at the like a force diagram here, we have the pivot sitting over on this side. Okay. There's the pivot. So then we have the force of the pivot going up, and then we have the force of the bucket down. Okay, so that's this guy. Then we have the force of the man lifting up over here on this side. So now we have to label some distances here. We have the distance that the man is away from the pivot, so D sub M. We have the distance that the bucket is away from the pivot, D sub B. So then all of our subscripts are kind of matching up. We have subscript M for the man. We have subscript B for the bucket. And then we have subscript P for the pivot. Okay? All that kind of making sense. So in this, we're trying to be very careful about how we're subscripting our things and also our labels. So we have F for force. We have D for distance. And then the subscripts M and B and P for man, bucket, and pivot. Okay, so now what do? We can calculate the force of the bucket very easily. So we have F sub B. We know that the bucket is holding 910 kilograms of mass. So we can go 910 kilograms times 9.8 meters per second squared. And that will give us 8,900 newtons after significant figures. Of course, our calculator will have a different idea of what it is, which we'll want to hang on to. Now, the distance of the bucket, so D sub B, we're told, where is it? 0.85 right here from the pivot. So D sub B is 0.85 meters. And now the distance of the man, I saw it first. Here it is right here. The distance of the man is 3.6 meters away from the pivot. So everything, notice, is kind of in terms of the pivot. How far away are we from the pivot? And why would we be doing that?
Because pivot's the origin.
So we're calling the pivot the origin, and that's where the torque is originating from, okay? So what are we looking for?
The man has to apply.
Exactly. What is the force that the man must apply? So that's the force of the man. We don't know. And also, what is the force on the beam from the pivot? That's the force of the beam. Not the force on the beam from the pivot. Okay, so that's F sub P. I just wrote a B. I need a P. Equals, we don't know. I'm going to go back and listen and count the number. I think it was 4 or 5 before we started.
Those are coughs, by the way, not sneezes. So.
Oh, really?
Yes, everyone thinks of that as a sneeze.
Well, who can tell the difference?
I can't because my sneezes were way different.
Okay. All right, so what we need to do now is do a sum of the forces and a sum of the torques, okay? So we need to do sigma forces, and these are all in the y direction. So we have the force of the man going up, so that's a positive. We have the force of the pivot. And we have also, that's positive, and then the force of the bucket, so that will be minus F sub B.
Equals 0.
This is not moving, so this is equals 0. It's not accelerating, so it does not equal ma, it equals 0. Okay, and so then we also have the sum of the torques. Equals. Now, all of these forces are being applied at a distance away from the pivot, with the exception of the force sub P, the force on the pivot, because that has a distance of 0. So we have, for the force of the man, we have to think about which way the man is trying to rotate the beam. That is in the negative direction because it would be rotating clockwise. So we'll write negative F sub M, and then the times the distance away for the torque. So that would be times D sub M. Then for the force of the bucket, we have to think about which way that would be trying to rotate the beam, and that would be rotating counterclockwise. So we'll write that's a positive rotation, so plus
F sub B
F sub B
times D sub B
to make the torque times the distance D sub B.
equals 0.
And this is not rotating, so equals 0.
How come the bucket's making it go in a positive direction?
The bucket is making it go in the positive direction because this force is trying to get the beam to turn counterclockwise, okay? The man's force is trying to get the beam to turn clockwise, okay? And the pivot is actually having the force applied directly at the pivot, so there is no torque there because there's no distance, okay? All right, so now what do we do? So do I know the force of the man? No. Do I know the force of the pivot?
Yes.
No. Do I know the force of the bucket?
Yes.
Yeah, I do. Okay. Do I know in the torques? Do I know the force of the man? No. Do I know the force of the bucket?
Yes.
Yes. Do I know the distance of the bucket?
Yes.
Yes. Do I know the distance of the man?
Yes.
Okay, so in the torques, I can actually now solve for the distance of the man, or the force of the man, okay? Because I know everything in the torque equation except for the force of the man. So what I'm going to do is I'm going to move the force of the man term to the other side so that it's positive and divide by the distance of the man. So I have force of the man equals force of the bucket, distance of the bucket divided by distance of the man. And I can substitute all of those numbers in. So that is, we figured out 8,900 newtons times the distance of the bucket, which was 0.85 meters, divided by the distance of the man, which is 3.6 meters. Of course, meters divides out here, and I'm left with just newtons. So the calculator will give us an answer, and then significant figures makes it 2,100 newtons. So that is the force that the man needs to apply to lift the bucket of 8,900 newtons, which is significantly less. It's pretty good. So that mechanical advantage there of the man using the lever of the beam is pretty significant. Okay, so now we can go back up to the force equation. We now know the force of the man, and we know the force of the bucket. We just need to know the force that is being applied to the pivot. So I can solve for force of the pivot. Almost wrote a B again. Equals, now I added force of the bucket, and I subtracted force of the man. So now I have force of the bucket, which was 8,900. And I'm subtracting force of the man, which is 2,100.
That makes me feel like I'm in grade school all over again. Or, 5th grade and stuff.
So 8,900 minus 2,100 is 6,800 newtons. So that's a kind of a basic problem on how we use both the sum of the forces and the sum of the torques to be able to manipulate and work between the two equations to come up with some answers. Okay? Okay, so which of these objects is in static equilibrium? Remember what is required. What can we rule out?
C.
C and D.
Definitely rule out C.
It's got a torque.
There is a torque, that's right.
A has a torque too.
A also has a torque, yep, because of this top guy here. So it's between B and D.
D.
D's the correct. It would be B's not correct because
There's not enough force.
on one side.
That's right. We have to have no torque. B and D both have no torque. However, we also have to have sum of the forces equals 0, so no net force. So B has a net force because they're all pulling the same amount, but there is a net force pulling to the right, whereas D would have a net force of 0. So the answer is D. All right, good job. Now, this one on the left side, consider the hammer resting on the supports A and B. What is the net torque at A and the net torque at B? What about at any point? So it's resting on the supports. We have the center of mass indicated here by our symbol, center of mass. We have the weight vector showing us down, and then we have a normal at A and a normal at B. What do you think?
I think it's 0.
Yeah, the net torque needs to be 0 in order for the object to be resting. Okay, if the net torque is not 0, then it's not going to be resting. Okay, this thing would rotate off; it would fall off. All right. So if the hammer is resting, then the net torque must be 0. Okay, unless it was like glued or something like that, right? So the net torque must be 0 at A, must be 0 at B, must be 0 at any point. So in order for the object to be in static equilibrium, the net torque about every point must be 0. So that means we can pick any point we want, okay? By that logic, we can pick any point we want as a pivot point for calculating torque. If we wanted to calculate the torque at A, we could do that. If we wanted to calculate the torque about the center of mass, we could do that. If we wanted to calculate at B, we could do that, okay? We can pick at any point that we want. So pick your pivot point as one that is either poorly defined, hard to come by is what that means, unknown, or otherwise simplifies the solution process. So now we can look at the girl on the rope climbing the face of the thing, or maybe rappelling, we don't know. But the torque due to the force about this point right here is zero. If she's just standing there, right, the torque about that point is zero. And that makes this point a good choice as the pivot point. Rather than choosing this point or any other point, this point right here is good to choose because it's poorly defined. We can't really figure that point out very well, so we choose that point. It's hard to figure that one out. All right. The other ones would be easier to use. So we would choose the hardest one. Okay. That way the calculations simplify for us. So that's what I'm talking about there at the bottom. She's in equilibrium as she rests on the rock wall. We make calculations about the hardest point to figure out, to simplify the math. Okay. So static equilibrium problems. Here is your strategy. We can use the fact that there's no net force and no net torque as a basis for solving problems. Remember, we're not moving, so there's no net torque and no net force. So decide on an object of interest. This should be an extended object with different forces acting on it at different points, and then decide on a pivot point. So your pivot point, remember, we want to make it something smart about which to compute torques. Next, model the object as a simple shape. So rather than the guy holding the bucket and a beam with a pivot, make it a simple shape, just the beam, and then mark where the pivot's going to be, and so on. So you're drawing your visual overview. Then add detail. So determine what forces act, where they act, the distances from the pivot, and so on. Then think about what forces act on the torques that they're going to create, what directions the torques are trying to get the object to rotate if it was rotating. And so therefore what signs they will have. And remember, this one's important, that the torques due to any forces acting at the pivot are zero. So that's why we're careful about the pivot that we choose. The mathematical steps are based on these conditions. F net equals zero and torque net equals zero. So then we write those equations for the sum of the forces and the sum of the torques. And then write or solve the resulting equations for whatever it is that you're missing. And then check to make sure that your result is reasonable, okay? That last stuff is stuff that we've been doing kind of all chapter long, or all semester long, I mean. All right, so a board weighing 100 newtons sits across two sawhorses like this. What are the magnitudes of the normal forces of the sawhorses acting on the board? So we know that there would be a normal force here and a normal force here, and we want to figure out what those magnitudes are for those normal forces, okay? That's the idea. So what do? Some kind of free body diagram. First, let's label this picture, okay? So we will have maybe normal 1, this guy, and normal 2, this guy. Since this is sawhorse 1 and sawhorse 2, I mean, they've already labeled it 1 and 2, right? So we'll call it normal 1 and normal 2. Okay, so then where is the center of gravity of this beam would be my first question.
It has to be in between the 1 and 2.
So of the beam, if the beam was just floating in space, where would the center of gravity of the beam be? Probably.
Middle of it.
It'd be in the middle, okay? So I'm gonna show that center of gravity. Okay. In theory, it would be right in the middle. Now, coming off of that center of gravity would be the what?
Weight.
The weight vector. Okay. Next, what I'm going to do is I'm going to put everything sort of in terms of the distance from the edge of sawhorse 1. I'm going to call that my origin, okay? Because it's going to be convenient to do that. Why?
Because it's a good pivot point. Everything's positive in that direction.
It's a good place to be, okay? We need somewhere to start. Would it make sense? Would it make sense to be coming off of the center of gravity for the beam?
'cause that's
Not
what
really.
distance is.
That's a bad spot. Okay, would it make sense to be coming off of the Sawhorse 2? Not really, because I mean, if the Sawhorse, if the beam tips, it's going to tip off of 2. Hopefully, you understand that, like physically, and that would be the pivot. But it's kind of a bad spot, also. Okay, the smartest place would be off of Sawhorse 1. All right, just because we can call that 0 and so on.
Black trash.
All right, so we're going to call this this spot here. This guy is going to be our pivot. Okay, even though physically we know that if this thing tips, it's going to tip around 2. We're going to call Sawhorse 1 our pivot. Okay, and then we're going to define everything in terms of our distances and so on is going to be coming off of Sawhorse 1. So then we need the distance from Sawhorse 1 to our center of mass. So that'll be D1.
1.5.
And then we need our distance from Sawhorse 1 over to Sawhorse 2. So we'll call that D2. And I'm doing this because I don't want to use numbers the whole time. I want to use letters. Okay? And then we also know already the distance from Sawhorse 2 over to the end of the beam. All right, so that's pretty good for our picture. In terms of from the origin or the pivot over to the center of mass, which is going to give us a torque, and over to Sawhorse 2, which is going to give us a torque. And now we can start labeling things, or writing down the inventory of what we have. So we have the weight. It says it weighs. That's not kilograms, that's newtons. So we already know 100 newtons. And then we have D1. What is D1? 1.5 what? Okay. That was because the beam is 3 meters. And then we have D2,
2 meters.
2 meters. We knew that already. How?
3 minus 1.
Right. All right. And what are we looking for here?
The normal forces.
The normal forces. So normal 1 equals, we don't know. Number 2, number 2. Normal 2 equals, we don't know. Okay. Now what?
We can do some forces.
Some of the forces and some of the torques. So we have some of the forces. Everything's in the y direction. All right. So that's going to be a positive normal 1, a positive normal 2, a negative weight because it's going down, equals,
0.
right? And we have some of the torques. And that's going to equal, what do you think?
It's going to equal 0. This is number one.
Well, it equals 0, yeah, but what are they?
Weight,
It's going to be
plus or weight minus N2.
Okay, so weight is going to be positive or negative?
negative.
This is negative because it's trying to turn us clockwise. So negative weight times
Distance 1.
D1. Okay, and then what else do we have?
Positive N2.
N2 is trying to turn us counterclockwise, so that's a plus N2.
D2.
D2. Anything else?
No.
No, because N1 is on the pivot, so it has a distance of 0. It's not included, okay? And that's why it's also very important that you put the pivot on one of these forces. Okay, and that equals 0 because this thing is not moving. All right, so now the question is, what do we know in these equations and what do we not know and what are we looking for?
Well, we know,
We know
weight,
everything
need to
except
know
for
the
we can
normal
find
forces.
N2, and then
Yeah,
find
in
N2, we can find
the
N1.
torque equation, we know the weight, we know D1, we know D2, we just don't know N2. So in the torque equation, we're going to solve for N2 right now. So I'm going to move the weight term to the other side and divide by D2 to get N2 by itself. So I have N2 equals, move the weight term, and then divided by D2. So there we go. The weight is 100 newtons. D1 is 1.5 meters. Divided by D2, 2 meters. So I notice that I have meters is gone and I'm just left with newtons. Also, I have 100 divided by 2, which is 50. So I have 50 times 1.5, which is 3 halves. I have 50 times 3 divided by 2. I get 75 newtons for N2. Okay, so now I can use the force equation. I have N1 needed, so I have N1, move the other guys to the other side, weight, and now minus N2. The weight is 100 newtons, minus N2 is 75 newtons. I get 25 newtons. There you go. Okay. Really, the hard part about these problems is figuring out where you should place your pivot. There is no wrong answer here, but there is definitely a better answer.
Yeah, easy answer.
The experience is going to help a lot once you figure out where the best place to put it would be. Okay, this second problem, I guess, well, this is the third problem, I suppose. A reaction board and scale are used in biomechanics to measure a person's center of gravity. So you can learn where your center of gravity is using one of these boards. A woman weighing 600 newtons lies on a 2.5 meter long 60 Newton reaction board with her feet over a fixed support. The scale on the right reads 250 newtons. What is the distance d from the woman's feet to her center of gravity is the question. So we have a bunch of stuff also in the drawing already for us.
I think our support should be that end.
The support should be the pivot.
Left. Yeah,
You're probably right.
probably. What the heck is that supposed to mean?
Means you're probably right. All right, what do we know?
Well, you know the weight of the woman.
Okay.
The weight of the board.
We have the weight is 600 newtons. We have W, right? But we also have W sub B, and that's the weight of the board. And that's a different center of mass also, notice in the picture. So we have W sub B, it was 60 newtons. Okay. And we have from the pivot, notice this is the pivot, and all of those distances are coming off of that pivot. So we have D, and the D is the distance from the pivot to the woman's center of gravity. That's the thing that we're looking for. And then they called the length of the board a capital L. And that was, what is it? 2.5 meters. Okay. And the force that's on the scale right now. Okay. Notice we have the end of the board over here on the scale. So that force right now reads 250 newtons. Okay. So that's all the stuff we know. The picture was already really good. We're ready to go. What do we do?
Some of the forces in the y direction.
Okay. Some of the forces in the y direction. What do we have?
You're gonna have the going with the weight plus
The force of the
So just reading from left to right in the picture, we have the normal force is up. We have the weight down, so that's minus W. But we also have the weight of the board down, so minus WB. And then we have the force up, so that's plus F
It's gonna equal 0.
equals 0. We're not moving. We're not accelerating, I should say. Okay, the sum of the torques. All right, from the pivot, we have the normal force acting at the pivot, no torque. We have the weight down.
Yeah,
So what is that?
that's gonna be negative. No, yeah, negative.
Negative. That's the clockwise torque. So negative weight
Of the woman
at what distance though?
at D.
At D. Okay. Then we have the weight of the board is next.
So plus weight
No, minus WV,
Oh, yeah, minus.
Yep, that's also
which is
Gonna
1.25 meters. That's the distance.
is it?
Yeah.
I don't want to use numbers right now.
be, so minus the width of the board times L.
WB.
It's not L,
Oh, it's gonna be half L.
half L.
Yeah.
So 1/2 times the weight times weight of the board times L. Okay, and then we're at F. So what is this one?
Plus
Plus.
F.
Just F?
D sub L.
So F times L.
Yeah, F times L. My bad.
Okay, that's all of the forces times their
Right.
distances equals
0.
0. All right. So now we look, what do we have?
We're looking for what?
Force. No, we're looking for D. Sorry.
We're looking for D. So
We need to solve for.
So we have F. We have W sub B.
Yep.
And we have W, so we should solve for the normal. No.
We can solve for D, can't we?
yeah, we know the length,
Yeah,
we
we know
know the
everything.
force, we know W sub B, and we know the weight of the woman. So we know everything in the torques except for D, and that's what we're looking for. So we just solve the torque equation for D and we're done.
Yeah.
So solving for D, so I'll leave the WD term. Actually, I'm going to move the WD term to the other side and then divide by W. So I'll have positive D equals negative 1/2 W sub B L plus F L divided by W. Just like that. And we can plug in our numbers.
Negative 1/2 times 60 newtons.
WB is 60.
Times 2.5 meters.
Okay. Plus, what is that? 250?
Yeah, 250 times 2.5.
2.5 again. So I could have done some work here and factored out the 2.5, made it a little bit easier. All divided by the weight of the woman, which was 600. Okay, newtons. Now, I have newtons in each term. So newtons, newtons, newtons. All those newtons are gone. I have meters plus meters up top. So the answer will be in meters, which is great. That's what I wanted. So this 1/2 right here and this 60 is going to make 30. I have 30 times 2.5, which is really 5 halves.
75.
75, but it's negative 75. And then I have 250 times 2.5, which is 125 times 5, 625. Over 600. And this is meters. Okay. What is this? 550?
600.
Isn't it 5?
550 over 600?
Yeah.
Okay.
Fours.
Right. Some kind of decimal then. What is it?
Should be 3/4.
No, not 3/4.
No, wait.
0.92 meters.
But it's a repeating one, right?
Yeah. So significant figures, we got 2. We'll call it 2. 0.92 meters is the answer.
11, 12.
Yeah, that sounds about
Yeah. But nobody knows what 11/12 is. So 0.92. Okay. 3-meter long ladder rests against the wall at an angle of 60 degrees with respect to the floor.
Ooh, 3069.
So that's a pretty easy picture. We can draw that. What is the minimum value of mu sub s, the coefficient of static friction with the ground that will prevent the ladder from slipping? Assume friction between the ladder and the wall is negligible. Okay, so
Doing F max.
I guess. So we can draw a picture of this. We have the wall. And we have the floor. Drawing a huge picture for no reason at all. And then we have the ladder, and it's making a 60-degree angle. All right, so there's our ladder. Now, what is going on with this ladder? Well, the ladder is going to have a center of gravity
Which is going to be right.
right in the middle of the ladder. And that will have a weight vector down, of course. Okay, now the ladder has 2 contact points. So that means we will have at the bottom where it's touching the ground, we'll have a normal force. And we can call that normal 1 because there's another normal force
Against the wall.
against the wall where it's touching the wall. And remember, normal is always perpendicular to the contact. So we have normal 2 here. Okay, now dimensions. We said this is a 3-meter long ladder. So this from here to here is 3 meters. 3.0 is given. I'm just writing 3.
We could find all the others, but I don't think we need to.
Okay, so we know this is a right angle down here, which means we have a right triangle situation going on. It's maybe not necessary. Maybe it is. I don't know. We would have then this distance here. That would be, we can call that d sub y. And we can call this d sub x if we need it. Okay. To the center of gravity, we could have this distance to the center of gravity. Since this is normal 1, maybe I call this d sub 1. I don't know what that distance is. I can always calculate it because it's the right triangle. Maybe I need, okay, instead of calling that d sub y, let's call that d sub 2. How about that? That would be better.
Okay.
D sub 2. Since that's normal 2 up there, we'll call that d sub 2. So I'm kind of leading us into where's the pivot?
About the normal 1.
Normal 1. Here's my pivot. If it's going to slide, we're going to pivot around that ground contact. Okay? So it makes sense to call that our pivot. Now, we probably should calculate then that distance d sub 1 and that distance d sub 2 because we're going to need it later, right? So then logically, d sub 1 is going to need some trig. So d sub 1 would be, if this is, let's say that the length of the ladder is L, capital L equals 3 meters. We know that, but let's just use L for now. Let's say d sub 1 then would be half of this length, right?
Yeah.
And which side are we using, sine or cosine? That's the adjacent. That's right. So that's cosine.
Yeah.
L cosine 60 degrees. Okay, and then d sub 2 would be what? And this time it's not half. We need the whole length. So this would be L sine 60. Okay, and the reason that I'm doing this is because I know I'm going to have a torque about that point, and I know I'm going to have a torque about that point. So I need those overall lengths. Okay? So now I need to do the sum of the torques and the sum of the forces.
Which?
So the sum of the forces in the x direction and the y direction. Sum of the forces in the x direction. What do I have?
You're going to have your distance.
I have normal 2.
And your distance x and 1.
What about missing one, actually? it said that a friction force between the ladder and the wall is negligible, but the friction force between the ground and the ladder is not. So if this ladder slid, it would slide to the right,
Mhm.
which means that there must be a friction force holding it back from doing that. So which way is the friction force going?
No, this way.
It's going this way. There is an F sub S here. Okay, so F sub X, normal 2 to the right is positive, but F sub S to the left is negative. So I have minus F sub S. Is this ladder moving?
No.
No. Equals 0. Okay, I need to do a sum of the forces in the y direction. What's going on in the y direction?
A lot. So we have normal up, so that's positive.
Normal 1, okay?
But it's at the pivot point, so you don't have to count it.
Well, that's
No,
torque.
forces I do, torques I do not.
And then
Oh.
we have weight down, which is negative.
Okay, so minus the weight.
And then we have,
Anything else?
well, those are all distances. Nothing else.
Nothing
Equals
else.
0.
Equals 0. Okay, sum of the torques.
So we have what?
Now remember where our
N2,
pivot is. Our pivot is here. So
Negative N2.
those guys don't count.
So the N2
Positive,
times V2.
positive W and negative N2.
Okay, so we have negative N2
Oh, D2?
D2, which we know is L sine 60. Okay, I'll put that in there in a second. And then plus, you said?
W D1.
Because that would be a counterclockwise torque. W D1.
Equals 0.
Good.
So we're trying to find normal forces.
I think we should stop before.
And we can substitute in now. We have negative N2. D2 is actually L sine 60 degrees. Plus W D1 is actually 1/2 L cosine 60 degrees. And this equals 0.
So we'd have to solve for N2. Right?
So yeah, do I know the weight?
Yeah.
Do I know the length?
Yeah.
We know everything.
I know sine 60, so I can solve for N2 right now.
It's going to be N2 is equal to WD1 divided by D2. So
And what happens to the L?
the L's goes between
I can divide by L and it's gone.
And sine over 60 and sine over cosine, that equals tangent.
60.
Tangent.
So yeah, let's move this guy, the N2 term over so that it's positive, and then I'll divide by sine 60 degrees. So I have N2 equals W 1/2 W cosine 60 degrees over sine 60 degrees. Cosine over sine is not tangent. Sine over cosine.
Cotangent.
This would actually be cotangent, or you can leave it like this if you wanted to. This 1/2 can stay up top, or you can put the 1/2, the 2 in the bottom. It's the same thing. And we can calculate this. Obviously, we have to stop here, so I'll pick this up with a short little finishing off the section tomorrow.